thank you so much for being the chairman of this third session. Enjoy.
Thank you, Francesco. So good morning to you all. So let's start out our third session. And let's start with the work by Hassan Rahim and Mukhtar. Sorry if I'm not reading this properly. And the work is entitled Experimental and Analytical Study of the Hyperelastic Behavior of the Hydrogel under Unconfined Compression. I've gone through the paper. It seems very good work, but a few comments or questions came to my mind. And so the first one is, I would like to ask if you could give us a few more details on the testing setup and procedures. And for instance, how was the stress and strain measured? Hello? Is anybody from the first paper online? It seems that someone is missing, and probably it will happen the same to the next paper, which is from the same author, which is Fracture Mechanisms in Human Teeth.
Maybe, Pedro, we can jump and then we can postpone these two papers at the end of the session.
At the end, we'll check again if they
Thank you so much.
Back. So let's move on to the third contribution by George Sakis. Is George online?
Hi. Yep,
okay,
I can hear you.
Okay. So your paper is entitled Polymethyl Methacrylate Structure Modification through Quantum Dot Nanocrystal Dispersion. It's nice work and a nice paper. I have one question. So what's the main application of this new PMMA material with this structure modification?
Okay, well, basically what we are trying to find out here is if the quantum dots, this scientifically new kind of material, is able to be used for medical applications like UV visualization and things like that. Since the quantum dots is very small and normally they are being purchased or fabricated in a liquid form or in small particles, you can't really use it as it is. So you have to have it on a substrate. So what we did, we basically chose the PMMA, which is thermoplastic, quite widely used thermoplastic, and it's biocompatible as a material because a lot of disciplines in medicine are using it, like ophthalmology, orthopedic surgery, and whatever. So what we did is that we fabricated this PMMA material with the MMA monomer. So we mixed them up at a very specific ratio. And then we added the quantum dots, which is luminescent material. So this is basically what we did, and what we tried to find out is if the dispersion of the quantum dots is quite even, because the light that is coming out of this material should be the same in each part of the material. So the dispersion was actually measured by the means that is described within the paper. That was it. Hello? Can you hear me?
Yeah, can you hear me now?
Yeah, I can now, but I lost you for. I don't know if you heard me.
Yeah, I heard you. I was saying that
Okay.
I have another question because, okay, you obtain a good homogeneity on the matrix, but nevertheless, there were some clusters of quantum dots.
That is correct.
Any design of experiments, for instance, try to improve, or what will be what can be the plan to solve this issue?
Okay, as you can see within the paper and the images, there are some at the same images. There are some clusters, and what we did is that the very last one we added at the very last PMMA material. We add in the experimental procedure the sonication. So we had a sonicate bath, and we immersed the material while it was in a liquid form, and then we noticed that the dispersion was much better, and we didn't have a lot of coagulation for the quantum dots. So what we are planning to do in the next experiments, I'll tell you, it's in our plans to increase the time of the sonication and experiment with other things like the polymerization of the material, as well as the stirring time and the vacuum that was applied for the degazing process. This is what we're planning to do in the near future to see if this will improve the dispersion and we have less aggregation of the quantum dots, because aggregation has always been a problem with this kind of nanomaterials. So we have already noticed that sonication really helps a lot, because with only 5 minutes sonication, we had much better image. But there are also other factors that need to be, let's say, improved.
Yeah, maybe you can use some design of experiments like Taguchi in order to get that improvement that you want, because you have a lot of parameters to play with. But
I understand there is a lot of things that need to be checked. This is a preliminary study, and I think that in the near future we will be able to do more work on it. But still, the results we already have are quite promising.
Okay, nice. So, any question from the audience? Okay, thanks. I think we can move on.
Thank you very much.
For the next presentation from Italy, Constanza is the author. So
yes,
the title
Constanza sent me an email. He will not be able to join us.
Oh,
so he had a problem.
So we should move on, because if nobody is attending from the paper, maybe you can move on to the next one. And the next one is a Portuguese contribution from Campilho. Let me open the file. Okay, and the title is Mixed Mode Fracture Toughness of a Structural Adhesive by the Single Leg Bending Test. So I've gone through the paper. One question or curiosities. Can you give us some details about this testing apparatus and the measurement setup or configuration that you use in such a test?
Yes, sure. Before all, hello everyone. Yes, this is the SLV test, which is a three. The text picture is very similar to the ENF test. So we have two supporting cylinders and a loading cylinder. And then to obtain the fracture energy of the in mixed mode of the specimen, we have to measure the load, we have to measure the displacement, and then we also need to measure three parameters. We need to measure the local separation between the two adherents. We need to measure the relative rotation between the two adherents at the loading line, and we also need to measure the shear displacement at the crack tip. With all these parameters, we can obtain the fracture energy in mode 1 and in mode 2.
Okay, so when comparing to the techniques that are already available, so what's the main contribution of these studies that you are carrying on when compared to the state of art for adhesive toughness measurement? And
when we are talking about the conventional methods, basically what we do is that we define only the fracture energies. In this respect to the J integral, we can also obtain the cohesive laws of the adhesive in tension and shear, and this is very helpful for us, for example, using cohesive zone modeling to predict the strength of structures in mixed mode. So the main advantage is that we can obtain the cohesive laws.
So do you believe that, okay, this achievement with this new test procedure can bring the adhesives closer to the industry or new industry?
Yes, I think so, because we have all the data that we need so that we can implement numerically the design process of these joints.
Okay, thanks. Any questions from the audience?
Hi, I have a question, if you don't mind.
Please. Yeah?
Hi there. I'm not if my voice is clear. Dr. Campbell, I just want to know what was the size of the specimen that you were doing tests on? And I have a couple of other questions.
Yes, the size of the specimen. Well, the length of the specimen is 230 millimeters.
Sorry, I didn't get you.
Sorry.
I think it's a little bit...
Can you repeat, please? There was some noise.
Okay, sure. With a total length of 230 millimeters. So we have a length between the cylinders of 200 millimeters. We have an adherent thickness of 3 millimeters and adhesive thickness of 1 millimeter.
So the thickness of the adhesive was fixed, 3 millimeter, yes?
That's 1 millimeter.
1 millimeter.
1 millimeter.
Another question, did you consider any curing parameters such as pressure or temperature for the adhesive, or no, it was everything room temperature?
Well, the joints were cured at room temperature, and but for the fabrication process, we applied pressure, but we had spacers between the adherents so that we could achieve the constant thicknesses that we wanted.
And this one was like a normal pressure by press, or there was, as far as the thickness is met, everything is fine, yes?
Yes, exactly. We had a jig to apply the pressure.
I see. Thank you very much. Just quick question and another one. What was the size of the element at the tip of the crack for your simulation? Thank you very much. I go out.
The crack tip? The size of the crack tip, as
Yes,
I
at the
understood?
crack, the smallest element size.
Okay. Well, we had a crack tip of about an initial crack tip of about 70 millimeters, 70 millimeters.
And the smallest element on the simulation?
In the simulation, it was 0.5 millimeters, the smallest length of the cohesive element. 0.5 millimeters.
Thank you very much. Thank you.
Thank you.
Thank you very much, Jamal. Any other question, please? Okay, thanks, Campillo, for the very nice work, as always.
Thank you.
Okay, we can move on for another presentation from Italy. Production issues in the manufacturing of titanium aluminum turbine blades by investment casting by Mondal.
Yes, can you hear me, Mr. Pedro?
Yeah.
Can you hear me?
Yeah, perfect.
Yes.
Perfect. Welcome.
Hello.
Main and, let's say, general question is, can you summarize, please, the main problems of investment casting of these turbine blades, and what's your proposal to solve those problems?
Yes, I would like to say it point-wise. The first would be the brittleness of the alloy due to its composition, but if we change the composition, we also change the material properties. So we don't have a lot of scope in that region. The second would be the presence of residual stresses after cooling the alloy, but this can be improved by changing the cooling rate and the design of the component. Thirdly, the reactivity of the liquid metal with the refractory material used in the mold at high rotational speeds, that's also an issue. Well, this depends on a lot of factors like the refractory material, the temperature, and etc. But in order to improve this, what we can do is we can apply a internal coating on the mold surface, or in order we can try to change the composition of the refractory material. But from our previous experiences and papers, I think the refractory material that we are using right now is best suited for this kind of application. Lastly, I can say that the presence of shrinkage cavities in the casting, which well depends on the composition, the temperature gradient, preheating conditions. But if these parameters have been already optimized with respect to the casting systems, so these are the things I can summarize it for you.
So in the manufacturing process, so you play with several parameters.
Yes, so there are a lot of parameters that needs to be considered.
So did you start thinking on a way to optimize this, like design of experiments, for instance, because you'll have a lot of parameters to play with, and you need to define the outputs that you want to work on?
To be particular with design of experiments, not so much, but considering our previous experiments and tests, we can say that depending upon a series of tests, we do have a particular set of compositions of the alloy that we consider during our experiments, and similarly, we do have a very controlled temperature sets with respect to the melting temperature, the cooling temperature, the melt, and the mold as well. So with respect to design of experiments, it's not so evident, but if you consider, we do have a set of all these parameters set for ourselves.
Mm-hmm. Thank you, Mondal. Is there any question from the audience? Okay, if not, I think we can move on. Thank you very much.
Thank you so much. Thank you so much, Mr. Pedro.
So the next paper comes from Bulgaria, and the author is Rizov, and the title is Influence of the Viscoelastic Material Behavior on the Delamination in Multi-Layered Beams. Is anybody online for this paper? I think so, at least this is here. So my question will be what's the influences of the viscoelastic behavior of the material on the delamination fraction in these multi-layer beam configurations subjected to creep? Victor, are you online? Okay, I think you can try it again at the end.
I guess he is online. He's shaking hand. I think you just.
I am.
Oh, you are here, but I was not listening to you.
Okay.
So, did you hear my question?
I didn't hear it very well.
Oh, okay. I'll try to repeat. So, I would like you to summarize the influence of the viscoelastic behavior of the material on the delamination fracture in this multi-layer beam configuration when subjected to creep.
Yes, our paper considers the effects of the creep on the strain energy release rate for a delamination crack in a multi-layered beam configuration.
Yeah.
And, an analytical solution is derived to the strain energy release rate by considering the balance of the energy in the multi-layered beam. The creep behavior is treated by using 4 viscoelastic models. The models consist of different combinations of linear rings and linear dashpots. Also, the strain energy release rate is derived also by differentiating the strain energy accumulated in the beam with respect to the delamination crack area for verification of the solution. And the solution is used to evaluate the effects of the creep behavior on the strain energy release rate. The analysis indicates that the creep leads to increase of the strain energy release rate. This fact shows that the creep behavior has to be taken into account when the delamination is analyzed.
Victor, just to complete, can you please explain the 4 linear elastic models that you use and why did you use those models?
I cannot hear you very well. I use simple analytical models. Simple analytical models, and actually an analytical solution to the strain energy release rate is derived in the paper by using 4 linear viscoelastic models.
Thanks, Victor. Is there any other question from the audience for this paper? If not, thanks for your
You are welcome.
participation. And now we can move on for the next one, coming from India, from Dalbir Singh, and the title is Mechanical Characterization of Composites Treated with Aviation Grade Fluids. Okay. So you are studying the influence of aviation fuel and lubricants on composites.
Yes, sir. Yes. Good afternoon.
Good morning here. Okay.
Yeah, it's okay. Thank you.
So where and when do you believe that such contamination can occur?
Yeah, can I answer now? Yeah.
Yeah, please.
Yeah. Yes, sir. Normally, like we are in the this is from Hindustan University, and we are having the aviation courses here, and we also have some aircrafts. And now, due to the weight saving things, the composites are used in the aviation in a big way. And then by seeing those things into the future, we gone for this work, and the main motivation was from the Amro sir and the Riz sir. They also done the same the work, but onto the glass fiber, but with the normal that lubricating oils. So we have gone for the aviation oils. That's the avgas 100 LL that's used in the piston engine, and then aviation turbine fuel that's used in any the turbine engine, let it be into the smaller aircrafts or bigger aircrafts. And then third one is the that's OX38 is nothing but also the Castrol 98. So in lieu of that, anyone can be used depending on to the manufacturer. So we have seen the effect of these lubricating oils onto the carbon composites. And then we have carried out the 3 tests, that is the impact, the tensile test, flexural test, and impact test. And out of like the test which we have done, we found out that like the OX38, which is the high performance lubricating oil, is affecting the material the most, which is used in this particular study. That's carbon fiber, bidirectional 090 200 GSM. And this is what the total, like we have seen that from the graphs and the PPT, you might have gone through it. It shows that like over a period of the time, since this studies was carried out in 15 days and 30 days and 45 days intervals. So we have tabulated the result, and then we came to a conclusion that the least is the effect with the 100 LL aviation, that is gasoline. It's nothing but almost all a refined petrol. And then the next the effect is from the aviation turbine fuel. That's and then the most they are affected by the OX38, that is high performance lubricating oil, and the percentage and all those things it's given into the presentation. Yeah.
Okay, so what's the conclusion? So is there a real problem? What would be the guidelines from your studies to
the guidelines from my studies are now, since the weight savings is the main, which is the core in the aviation. So and we have seen that like in the other areas where like say flight controls and the primary structures, secondary structures, composites are already being used extensively. So the area where just we are pointing it out that okay, they can also be used as a fuel tanks. So in that area, like we are proposing, okay, this can be a substitute, but provided there are like a little bit more research to be carried out so that this effect can be minimized. So I think in the next study we are going to also do, since we are using phenolic reagents, we are also going to do the temperature study also. So with the different temperatures, though, in the days to come, we will see like what is the effect even with the temperature, because once the lubricating oil, after once it do the lubrication, there is a heavy heat is generated into the bearings, and once it comes down, it's come with the temperature. And since temperature effect, and then this what we have studied, and then like it becomes a full study. So we are in the process of those studies also. So that's what. Yeah.
Okay, thanks for your answers. Then any other question from the audience for this paper? If not, thanks.
Thank you, sir. Thank you so much. Yeah.
And we can move on to the next one from Jamal Jamali. For sure that is online and active, which is very nice. And the title is Woven Carbon Fiber Epoxy Fracture Testing. I saw you in your work that you use CTS specimens. Did you load those specimens on mode 2, pure mode 2?
Hi there. First of all, I'm attending from the American University of the Middle East in Kuwait, Middle East. I'm Iranian. However, moving around. Yes, we were trying to study mixed mode testing for mixed mode behavior, different type of polymer composites. We have just started moving from UD composites to plain weave composites. This is actually along the path of the work I have started before. I was trying to study the translaminar fracture of UD composites, and then I came with an idea of how to predict this kind of fracture behavior, and then I moved to mixed mode, and after that my idea was going towards plane wave. This is a very preliminary steps towards that direction. So we want to understand more about fracture and mixed mode fracture of woven composites, and we started with carbon fiber at first, 2x2 twill carbon fiber. As I told you, this is the preliminary, and we only studied one pure mode 1 and 15-degree angle mixed mode 1, 2, not mode 2, just to clearly answer. Okay. This will be as the progress of this work.
Yeah, that was another question. Why did you choose this 15 degrees angle only? But now I understood that you are working on it. It's just the first one.
Exactly. You know, it took time so to make the fixture, prepare the specimen, and then finally do the testing. So we started from 0 and 15, and we are continuing this with the round of students that I have. So that was like the main idea. So it's still going on.
And are you using any optical technique to understand the behavior of the material during testing? Like DIC or?
No, we are. I think that's part of the new thing in this work. We have our own way of displacement tracking. We don't have DIC unfortunately here, so we try to do the same concept of DIC, make tiny speckles at the tip of the crack, and then capture that with camera and try to adjust it with the reference size and get it. Of course, there is an error when we do it, but it's very simplified. It's super cheap, and for us that we don't have DIC for now, it's working. It's kind of working, I can say.
Thanks. You work, at least the first steps look very nice and interesting, in particular to use this research solution for loading the specimens. So is there any other question from the audience? Sorry. No. We can move on. I think we have a feedback problem because Professor Paulo just joined us here and needs to mute your microphone.
I mute my microphone.
No, not you. Professor Paulo Reis that is here with me just arrived. Oh, okay, now it's okay. Now it's okay. So I think we can move on.
Thank you, Dr. Pedro. So I mute my microphone and there. Thank you.
Okay, thanks. So let me open the next one.
Não, eu estava a dizer, não me admirava nada que fosse ao contrário. Ou seja, não me deixar.
Just a moment. Okay, now we have Markides from Greece with a work entitled Similarity of Fluctuations of Acoustic Emissions in Natural Time. Okay, so I have main questions. What would be the main application of your findings, really? This is a bit parallel to the work that I'm working on, so I need your help to understand a bit what you are doing and the applications.
Yes, our work is a sub-result, let's say, from an earlier publication where we calculate the energy of acoustic emissions in natural time. Unfortunately, it wasn't published up until a couple of weeks ago. That's why I couldn't reference it more. What we're doing here is that we take the energy of the acoustic emissions, we calculate the kappa 1 variance of natural time, and then we compare it with other systems that are approaching criticality or failure. I think the approach of treating the acoustic emission energy as a node parameter is much more universal, and doesn't take into consideration the geometry of the specimens. And we treat different specimens of different geometries as the same. That's why in our work we compare it with magnetic models, and there have been many publications which I cite that this approach can be used in a variety of systems, such as cardiograms, and in general many different types of systems. So I hope I have answered your question. Yes.
So you are doing this test on let me see.
On marble specimen, on marble and cement model.
Yeah.
Yes.
But you are mentioning also in your work that you can, let's say, extrapolate these findings or technique for bridges and monuments. How can you extrapolate what you are doing to bridges, for instance?
The main our team is heavily involved in the restoration of Acropolis, of the Parthenon.
Yeah.
So what we do is we examine specific parts of the monument, and we mimic, let's say, this specific structural element and the stress that it is induced by the monument itself in that specific part. That's why we have, for example, the notched specimen, the small marble notched specimen. And what we hope is to, apart from the Acropolis, to do it in bridges. We want, for example, to measure an epistyle. We cut a specimen in a smaller scale, but with the same physical properties, with the same stress, the same forces being applied, and we can calculate, because that's the end goal, let's say.
So it's mainly for laboratory applications, or you can go for in-field applications?
In the present moment, it's for laboratory applications. What we actually proved now with this work is that the order parameter for seismicity, that the kappa 1, the variance kappa 1 in natural time, which it was first used for seismicity, is also applied for acoustic emissions due to their similarities between the earthquakes and acoustic emissions. So yes, first we went a bit backwards. First it was proven for field applications, and then we proved it also for laboratory applications.
Okay. So thanks. Is any question from the audience? If not, okay. Thanks again.
Thank you very much
and for the participation.
If you have any questions, feel free to email me. And I hope to see you in Athens for the Mediterranean conference we go organize.
We'll do our best. We'll do our best. Okay, so let's move on to the next one. Open here. So this one coming from Russia, and is the effect of modifying dopes on the mechanical properties of epoxy coatings affected by thermal cycling. So my first question will be really what's the main application of these epoxy coatings, and how can this thermal cycling occur?
Good day. For example, such conditions occur when operating structural elements in Arctic conditions that are located near cyclically operating thermal installations. Here, the heating of the surface is alternated with cooling.
And another question is, what's the main reason behind the increase on hardness when using the titanium dioxide doping, and why the hardness decreases when using the other two dopings, the zinc oxide and silicon dioxide?
I don't know, but it's possible that the oxide modifier in epoxy resin manifests itself not as a different filler that changes the strength properties of the material, but as reactive component that forms a certain set of intermolecular interactions. To clarify the specific cause, additional research should be conducted with specialist chemists. That's all now.
Okay, so this is, let's say, an ongoing work.
Yes.
Okay, there are still some open topics to be further explored.
What is the installation? Explain this. I'm sorry, I don't listen.
Yeah, if as far as I'm understanding, this is an open work, it's ongoing work that you are still working on, and that there are some things still to be understood. Yeah.
Yes, it is an investigation on the future application.
Okay, so is there any question from the audience? If not, I think we can move on. Thank you very much, Sergey, for your participation.
Thank you.
Now we can go back to Greece. Work by Markides, enlightening the role. Okay, hi. Enlightening the role of critical parameters for the determination of the tensile strength by means of the circular semi-ring test. So first question is really, what's the main advantage of this circular ring test, semi-circular ring test?
Yes, actually we have been working on this project for the last 4 or 5 months. I think it's a relatively new try of our team, and actually we try to confront the problem met in the Brazilian disc and the circular ring test, which has to do with when of course you use it in order to obtain the tensile strength of brittle materials. And the main problems of this existing test, of course widely known and very good test, the main problem of this test is that as the contact region where the external load is applied, we quite often see premature fractures. So this somehow violates the precision of the tests and the results taken, and you have to implement a lot of tests in order to keep the better experimental protocols. With this try, our goal is to, and actually this is the case, is that the fracture load through the circular semi-ring test is highly reduced. Actually, as you can see for a diagram here in the I think yes, in the last on the last slide of the presentation, we can obtain the tensile strength of marble by pressuring it with a force of an overall force of 170 newtons, which of course it's a very low fracture load that cannot cause premature fractures at the contact region. So actually this is the main advantage of this new approach, we hope, and of course again the tensile strength, actually the stress field at the point where the tensile strength is expected to develop is unidirectional, as in the case of the semi-ring test, contrary to the case of the Brazilian disc test, where we have at the center of the disc two-directional tensile, two-directional stress field. So the main advantage is the low fracture load, and of course the unidirectional stress state at the point the tensile strength is expected to develop.
Okay, I would like you to comment one thing that I read on your manuscript. You mentioned that for brittle materials, the test should be adopted as a function of easiest laboratory implementation. And you mentioned something that it can lead to different fracture loads. So I got a bit confused on this section. So you are saying that each laboratory should use the technique that best fits their setup?
Yes. You mean in the paper?
Yeah, in the paper, yeah.
In the paper submitted, yes. Because in the literature we have noticed that there is a point of conflict regarding whether the Brazilian test or the ring test or in general all these tests are actually depict a mechanical property of the material, or is just an experimental result. And as we can, we eventually believe, and of course the experiments will show us the truth, is that the design strength as it is obtained through these tests, indirect tests, apart from the direct tensile tension test, so the design strength is taken from these indirect tests is not eventually an experimental result. Of course, if we put aside the side effects, and it's not an experimental result, because as we can see in the formula, in the analytic formula we have obtained, and previous formulas, Hobbes, for example, as it is discussed, is criticized by Hudson. Actually, in our formula, you can see that there is the design strength is obtained in terms of the external applied load. So whether we use, for example, the Brazilian disc test or the semi-ring test or the ring test, you have always in mind that the design strength will be one. What makes the difference in this test is the externally applied load required in order to obtain to fracture the specimen, and that is the conclusion. The conclusions point out at this point of our study that eventually the design strength as obtained from the Brazilian, even the Brazilian disc test or the ring test or the semicircular ring test, is not an experimental result, but is an inherent property of the body, of the material.
Okay, thanks. Thank you very much. Then, there are any other questions from the audience? If not, thanks again for your participation.
Thanks for the hospitality. We are looking forward to see you in Athens.
I must go there. Okay, thanks. So let's move on. For the next one, from Italy, Constanzo Bellini. Damage analysis. Oh, hi. Damage analysis of a glare laminate subjected to interlaminar shear. So, can you summarize the advantages and disadvantages of glare versus these glass fiber reinforced polymers?
Yes, of course. Indeed, with my study, I can say not so much about the difference, because in this study I analyzed only the interlaminar shear strength. So I can say something only about the delamination. Obviously, this is just a little part of a wide study concerning the comparison between these two materials. So there are some other tests that are ongoing, and on the basis of the result of this specific study, we can say that there are not so much difference concerning the delamination. In fact, we wanted to study the delamination because glare is a material composed by two materials: composite, that is a composite with all these problems, and aluminium. And we wanted to study the lamination at the interface between this material, because this zone could be a zone with such problem. But we have seen that the delamination starts not from the interface. Indeed, we have used an adhesive, a structural adhesive at the interface. But the problem is the delamination starts from the composite material. And we carry out other experimental tests, for example, tensile tests or 3-point bending on long specimen, so flexural test, to study the other properties. And so we have to carry out other tests. From this test, the behavior is more or less the same as concerns the delamination behavior.
Okay. Yeah. So you carry out not only tests on 25 millimeter specimens, because what I would like to ask next is if you can extrapolate these 25 millimeter length specimens, the results that you present in your manuscript, to real structures, because these specimens are really short.
Yes, the specimens are really short because for the purpose of this study, so for the interlaminar shear strength, the ESTM standards indicates this dimension. So you need a short beam to extrapolate the interlaminar shear strength. Obviously, for other properties, you have to carry out other kind of test. So these properties, these specimens are suitable only for that mechanical properties. So for a whole characterization, you need other tests.
Another question is, when you show your results for this interlaminar shear strength, there's the standard deviation for the non-glare material is quite larger than for glare. Why?
Yes, we compared the glare with the GFRP, so with the glass-based composite material that is a constituent of the glare. And I can say that the delamination starts from a defect. And maybe that we have a higher standard deviation because on GFRP there are more points, more defects, so more points, more starting points for this delamination. So we think it's a problem of probability.
Okay.
This is the problem, the question.
So, is any other question from the audience? If not, thanks for your answers.
Thank you.
So we can move on to a presentation by Santos from Portugal. Hybridization effect on the bending properties of flux composites.
Hello, good morning, everyone.
Good morning. So since you are using a green epoxy resin, what is the main application foreseen for this?
Hello. For example, structural application where mechanic properties are not relevant, or applications in direct contact with environments or people.
Can you repeat, please, because I couldn't understand.
Structural applications where mechanic properties are not relevant, applications in direct contact with the environment and people.
Okay. So can you talk a bit about this hybridization? How does it decreases the viscoelastic behavior of these natural fiber reinforced composites?
Hybridization is the different arrangement between natural flax fibers and synthetic fiberglass fibers. As the number of glass fiber layers increase, the viscoelastic composition decreases. It means that natural fibers has a much more viscoelastic behavior than synthetic glass fiber.
Okay. Any other question from the audience? If not, thanks for your answers.
Thank you so much.
Just let's go back to check if Al Mukhtar is online now. It seems not so. So the session is over now. So it's time for lunch. Thank you all for your participation and see you in the afternoon.